Be your chemistry teacher, and today we are going to look into the radiant energy, and this is under the UV visual spectroscopy. The question is, how relevant is the radiant energy? Remember that you cannot do without the light source that is required whenever you want to carry out the IR or the UV spectroscopy experiment. Now, the light source is where the radiant energy comes. Simply put, radiant energy is simply that particular transmitted radiation as the electromagnetic radiation. That is the energy transmitted as electromagnetic radiation. That is all. That is what radiant energy, and that energy transmitted as electromagnetic radiation can be calculated. Remember that we said that whenever there is any experimental procedure for UV visible spectroscopy or IRO, there must be a light source. That's the first thing. That light source, which is either going to be a tungsten lamp, if you are going to use that, or it's going to be maybe a sort of a global source or any other one, as the case may be, depending on what you are trying to carry out, UV or IR. And remember that we also told ourselves that there is these radiations that build up the electromagnetic radiation or spectrum, ranging from your gamma radiations up to your radio waves. Yes, we said that. And the UV visual spectroscopy, the IRO, are all part of it. Now, do not forget that this class, you need to share this class. You also need to do what? Also need to ask your friends you are sharing to be part of it by simply hitting the subscription button. Even at my Facebook page, Dr. B Chemistry Classes, you also have to share and let them hit the follow button. You can like, you can also comment, as the case may be. Now let us see how we can be able to determine the radiant energy, which we say is the energy transmitted as electromagnetic radiation. Now, know that E is equals to HV, and this equation is simply an electromagnetic radiation equation that defines energy. Why this is energy? This is simply the Planck constant. The Planck constant. The Planck constant is given as 6.62 times 10 to the power minus 34. You must know this value. Okay, why this, of course, is your frequency. Why this is your frequency. You must take note of this. Now, this Planck constant and the frequency build up what you define in that product as energy. But there is also another equation which simply says that C is equals to H is equals to V, okay, times what? Times lambda. Now there's an equation of this form that says C is equals to what? Is equals to V times lambda, where of course C is your speed of light. Is your speed of light. And speed of light is always given as 3 times 10 raised to power 8. That is the speed of light in per second. Okay. Right, so this is speed of light, and it's given as 3 times 10 raised to power 8 per second. And this is your frequency, while this is your lambda, and this is your wavelength. This is your wavelength. Now, do you know that we can get the value of V, which is the frequency, from this equation by simply making the sort of formula? Now that means that we can say that V is equals to C over lambda. Of course, we can say V is equals to what? C over lambda. Yes. And if we have this, we can substitute this to take this equation, to take this value. We can substitute this C over lambda to take V, which is frequency. And when we substitute equation 3 into equation 1, we are going to have what? It means we have E is equals to H times C over lambda. That's what we have. If we substitute this equation into here, this V will change to C over lambda. And when this happens, we have this equation. This equation can also be written as E is equals to H C over lambda. Of course, that is just this times this is Hc over lambda. And this equation can also be written as E is equals to 1 over lambda if we say H and C are constant. Of course, since we said H and C are constant, H is the Planck constant 6.62 times 10 to the power minus 34. C is a constant, which is what which is 3 times 10 to the power 8 per second speed of light. So if these two are constant, we can simply define this as radiant energy equals to 1 all over what lambda. Now this is the equation. This equation here is the equation that defines what the radiant energy. So at any point in time, you are given a question to calculate the energy of radiation, the energy that is transmitted, okay, the energy that is transmitted in the course of any spectroscopic analysis, say UV visible or IR. That particular energy that is transmitted is simply the radiant energy, and the equation that allows you to determine that particular energy transmitted in the course of any spectroscopic analysis is either of this equation. If you follow my class, the next class we are going to have after this is to see how we can be able to calculate some parameters that govern UV visible spectroscopy or IR spectroscopy using any of the equations we have put here. And very importantly, the radiant energy or energy transmitted as EM or as electromagnetic radiation will be part of it. I'm sure that you have learned something from here. You've been able to understand how you can be able to get your transmitted radiations, or you call them your radiant energy, in the course of any spectroscopic analysis. We are going to put it into action with numbers and see how we're going to calculate it in our next class. I want to thank you for being part of this class. Please do not forget to share this class. Do not also forget to like, to comment. And when you share, don't also forget to ask your friends, your colleagues to subscribe and also to follow my class. Until next time, it is bye for now.